G'day, in this video we're going to be exploring Einstein's postulates and frames of reference. In this video we're going to be starting to work on the fourth and final dot point for this module. And in it, we're looking at how the behavior of light has impacts on how we understand time, space, and matter. What we're referring to here is Einstein's theory of relativity, in particular, his theory of special relativity, which is the one that we're going to be focusing on in this inquiry question. The key aim of this video is to understand Einstein's two postulates. These were concepts that framed the basis for special relativity itself. And from there, we're going to start to unpack some thought experiments that justify Einstein's ideas and his theory for relativity. So in order to understand this, we're going to have to review our understanding of frames of reference because it plays a vital role in understanding the theory of special relativity. We're then going to introduce the two postulates and how they connect to special relativity themselves, and again, unpack some thought experiments. Frames of reference is nothing new. We've been looking at it since Module 1. Essentially, the concept here is that we can make observations of the universe from different locations, and depending on where we're observing from, the observations that we actually make, the measurements that we make, may differ from each other. So in this scenario here, what we see is a car traveling down a road and there's two observers, one on either side of the road. Now in this scenario, they might measure the speed of the car to be the same, but their velocity could be measured differently. This observer observes a car traveling to the right, whereas this observer observes a car traveling to the left. A solution for this discrepancy is to use directions like cardinal points rather than describing direction based on the person's frame of reference and the location from which they're observing. When unpacking special relativity, we're going to be looking at frames of reference, which a lot of the time are what we describe as inertial. So it's really important that we also understand what that means too. At its core, to be an inertial frame of reference, you need to be in a frame of reference which is not accelerating. Now, just because you're not accelerating doesn't mean that you're stationary. This also includes frames of reference that are traveling at a constant velocity. In this scenario here, both frames of reference A and B can both be considered inertial, assuming that the train is moving at a constant velocity. For the person in reference frame A, they observe the train moving to the right. And for reference frame B, because they're in an inertial frame of reference, their measurements and observations reflect the idea that they are actually stationary and that person A in the other frame of reference is moving instead. The same is true if you were driving in a car, say, at a constant speed. What we're actually observing is the world moving around us and us remaining stationary. Now, our brain's a little bit smarter than that, and because it knows that we're in a car and that the world is moving around us, it knows that stationary objects like trees, for example, aren't actually moving. And so it's a little bit difficult for our brains to reconcile the fact that what we're perceiving is kind of the opposite of what we know and understand, yet it is still true. This phenomenon and concept is important because what it suggests is that if you are in an inertial frame of reference, you can't actually do an experiment within your frame of reference to prove whether you are stationary or moving at a constant speed. The only way that you can tell is by looking at your surroundings and see the world moving around you. Or if you're stationary, not moving around you. And it's this concept which we will look at a little bit later. We've already analysed the concept of frames of reference in Module 1. Here we were looking at relative velocity in one dimension, and the idea that if you've got two objects moving in the same direction or directly opposite directions, observers in both frames of reference will observe the scenario very differently. So if you have car A and car B and one person in each, car A will observe car B moving backwards, and car B will observe car A moving forwards. And even though they're traveling at 10 meters per second and 7 meters per second respectively, the difference between these two speeds is 3 meters per second, which means that both observers are going to either see one car moving ahead or one car moving backwards or behind at a rate of 3 meters per second. The key point here being that the mathematics that underpins these observations is all dictated by who is observing in what frame of reference and what are they observing around them. And by being in two separate frames of reference, it's quite likely that you will observe a scenario very differently to another person in another frame of reference. These techniques that we learnt in Module 1 are known as Galilean transformation. We've applied this transformation in many other scenarios across the majority of modules in this course. Essentially, a Galilean transformation is resolving or calculating the resultant motion of an object when there are multiple factors or multiple vectors at play. Sometimes this results in motion in one direction, other times it results in motion in two dimensions. The scenario in this diagram is actually quite similar to a scenario which we'll be looking at later for one of Einstein's thought experiments, which helps to explain special relativity. I want you to imagine that you are inside a moving box, and the box is traveling at constant speed. And while inside this box, you pick up a ball and throw it up and catch it. What you should observe is essentially something like this. The ball travels directly up, the ball travels directly down, the ball doesn't move in the x-axis. This is to be expected in a scenario where we are moving at a constant velocity, and again reinforces the idea that you can't complete an experiment inside an inertial frame of reference to prove whether you are moving or stationary. However, for an external observer, let's say we are standing outside and able to see inside the box. Maybe we've got X-ray vision or something like that. What we would observe in this situation is the ball not just traveling up and down, but also in the x-axis. Essentially, what we would see here is a projectile reflective of what we looked at in Module 5. This again is reflective of a Galilean transformation in which components of motion in the x and y axis are resolved. With our understanding of frame of reference and Galilean transformations, we can begin to discuss Einstein's two postulates, as well as the concept of special relativity. Essentially, a postulate is a statement or idea which is widely regarded as true. In other words, these are concepts which scientists generally agree on. His two postulates were about relativity, as well as the speed of light. His relativity postulate states that all motion is relative, and that a measurement of motion is dependent on the observer's frame of reference, as we just talked about earlier. He also suggested that the laws of physics are maintained and are equivalent in all frames of reference, the consequence being that you cannot do an experiment in your own frame of reference to prove whether you are moving or stationary, and that Galilean transformations resolve any differences in observations between the observers in the two different frames of reference. Essentially, it's all the things that we've already been reviewing. The second postulate is that the speed of light is constant, and this was based on the work of Maxwell. It's these concepts that we looked at the beginning of Module 7. And essentially, Maxwell was able to resolve equations both about electricity and magnetism to find a connection and a relationship between the two, to develop the understanding of light being an electromagnetic wave, but also that mathematically the speed of light was constant, that the permeativity and permeability of free space, both constants found in our electricity and magnetism formulae, were the only values present after everything was cancelled out that could describe C. So both of these being postulates of Einstein's special relativity, Einstein was emphasizing that both had to be true. However, based on the current understanding of physics during this time, he was able to assert that the two postulates in certain scenarios no longer worked with each other anymore, and that essentially our understanding of physics had to change if these two postulates were true. This brings us to Einstein's thought experiments. In this first experiment, we're looking at the idea of the behavior of light in a scenario where the light source is traveling in an object that's traveling near the speed of light. And so Einstein asked a question: would I see my reflection in a mirror if the mirror and I were traveling on a train which was moving at the speed of light? According to the concepts of relativity, this question's actually quite easy to answer. The answer has to be yes, because if you are in a moving object in an inertial frame of reference traveling at the speed of light, and you shine light towards a mirror, it needs to bounce back. Otherwise, you would be able to conduct an experiment to prove that you were moving and that you weren't stationary. In other words, inside your internal frame of reference, physics exists as it usually does. Light travels at the speed of light towards a mirror and travels at the speed of light towards the observer. No differently to if you were to do this as a stationary observer. However, this then begs another question. What if you were in an external frame of reference? What if you were standing outside the train? What if you were watching the train pass as the light was being shone? Would you see the beam of light traveling at the speed of light or double the speed of light? A Galilean transformation suggests that the light would be traveling at double the speed of light. It would be the speed of the train plus the speed of the light. Except for Maxwell's equations to be correct, the speed of light must always be constant. So the answer here is it has to be C. Both observers observe the light traveling at the speed of light according to Maxwell's equations. And this is where we start to see contradictions between the two postulates. How can the speed of light be constant and the principles of relativity be upheld? And it's this contradiction which is solved by Einstein's theory of special relativity. It's best seen if we do the same light, mirror, and train thought experiment, but change it up ever so slightly. What if we did this experiment again, but the mirror was above the light source instead of across the train along the carriage? What if we shone the light up, say, at the roof, where there is a mirror? This scenario is quite similar to the ball throwing experiment that we talked about a little bit earlier. The observer on the train will just simply see the light travel up and travel directly down at the speed of light. However, if you're the external observer, you'll be watching the light move upwards, but also watch the train move across. And therefore, by Galilean transformation, you'll observe the light travel diagonally towards the top of the roof and then diagonally towards the floor again. So in this version of the experiment with the ball, both observers would measure the ball, leave and return to the hand in the same amount of time, even though the ball is observed to travel at a different velocity. It's also noteworthy to talk about here that if we're measuring the same time, but they're traveling at a different velocity, that the balls would therefore also travel a different distance, which makes sense. Either the ball is traveling like this, or it's traveling like this, clearly to very different distances. There's some similarities and differences in the light version of this experiment. Both observers would measure the light traveling at a different distance. That's still the same. However, things flip around a little bit. If the speed of light is constant, then they can't travel different distances in the same amount of time. Instead, they must observe light travel for a different amount of time for this to actually work. Because observer A watches the light travel over a shorter distance, it will also watch the light travel for less time than observer B, who observes the light traveling for a longer period of time. What we're now suggesting here is that time is not absolute, that in every frame of reference, we don't necessarily measure time the same way. And this is the element of Einstein's special relativity, which is really confronting in a lot of ways, because we as humans don't necessarily observe and see that every day. So it does feel quite backwards to it, yet this thought experiment proves that it must be true. We'll look at quantifying this relationship and actually mathematically explaining how this works in the next lesson. A couple of points before we leave today. I want to talk about the idea that Einstein's theory of special relativity is referred to as special. I want to talk about why that's the case. Essentially, special relativity explains what classical physics cannot in scenarios where an object is moving at a significant portion of the speed of light. Essentially, this theory of special relativity is able to explain what classical physics cannot. It's able to account for some weird things that happen when objects are traveling at very high speeds. But there's a limitation to this theory of special relativity. It only works when we're observing in inertial frames of reference. Therefore, we refer to this as special relativity because it only applies to special circumstances. Please note that we're going to be focusing on special relativity in this inquiry question, but there is another type of relativity, general relativity, which goes a little bit further than what we're going to be learning about and is outside the scope of the physics course. And what general relativity does is account for non-inertial frames of reference and therefore applies relativity in a general sense or in all scenarios and cases. The other thing that I want to address today is whether or not being on Earth, standing stationary on Earth, counts as being in an inertial frame of reference. And the answer is kind of yes, I guess. There's arguments for yes and there's arguments for no. So I want to break that down too. So the Earth itself is constantly traveling through the universe and does so at large speeds. The Earth rotates, the Earth orbits the Sun moves through the galaxy, and the galaxy moves through the universe. However, it doesn't really speed up or slow down as it does that. The magnitude of the Earth's velocity is, relatively speaking, constant. This implies that the Earth is, therefore, an inertial frame of reference. If you're standing on the Earth, your speed really isn't changing. Except that's not entirely true. For example, when analysing the orbit of the Sun, because we're moving in a circular path, are therefore experiencing a centripetal acceleration, which is something that occurs for the other movements as well. But when you do the math and you look at the velocity of the Earth as it orbits and the radius through which it's orbiting, the amount of acceleration experienced is quite small. And what that means is technically the Earth is non-inertial, but these accelerations which are occurring as the Earth is moving through the universe are quite low, and we physically really can't perceive them. It's not like we're slamming on the brakes or doing a really hard corner in a car and our whole bodies shift towards the left or the right. None of that's happening due to the Earth's movement. Therefore, we can kind of estimate or approximate the Earth to be an inertial frame of reference, but technically it is near inertial. However, when we're talking about concepts and calculations, we will assume that standing still on the Earth is considered an inertial frame of reference to sort of make our concepts work. Thank you very much, everybody. In the next video, we're going to be looking at the concept of time dilation and length contraction, the consequence of the thought experiments that we unpacked in this video. But until then, have a good one.